Hi everyone, Mike here. Non-local reality, better known as spooky action at a distance, is a very strange concept that comes to us from the world of physics, specifically quantum mechanics. And it's not much of an exaggeration to say that it claims that two entangled particles, no matter how far apart they are, can actually communicate with each other when one is measured. This is a very strange concept, and I plan to be arguing against it in this video. I'm going to be doing it at a very high level, and I'm going to be doing it rather quickly so that we can get the entire argument into our heads in one picture. So let's get started. In a Bell Theorem experiment using entangled photons, the quantum mechanically predicted function that describes the probability that the two observers, Alice and Bob, detect the same outcome is cosine squared theta, with theta being the difference angle of the polarizers used by the two observers. Now, a Bell Theorem experiment is an experiment that's designed specifically to generate what is considered non-local or spooky action at a distance data. In the case of using entangled photons, that data will look like cosine squared theta. In this case, what they're saying to us is you cannot construct a model of reality using only local reality that will end up with cosine squared theta as the correlation probability. Number two, if the experiment is repeated using random pairs of photons with the same polarity in place of entangled photons, then that same function becomes 1/2 cosine squared theta plus 1/4. So what we've done is we've repeated the exact same experiment and just changed one thing. And that is, instead of entangled photons, we're going to be using random pairs of photons that happen to have the same polarity. And since we're using random pairs of photons, all the data that we're generating here is going to be of a local nature. There's nothing spooky going on here, and there is no entangled photons. What's notable is that the cosine squared theta is one of the terms. It's 1/2. And we also have a constant of 1/4. So we have the two terms. Point 3. The above two statements are considered true, quantum mechanically predicted, empirically verified, and can constitute reproducible phenomena. In other words, we are going to consider both of these as facts that need to be considered when establishing a world view. Now we come to the good part. Part 4. We now introduce a property assigned to photons that we will call bias. It has two values, up and down. Photon can have either up or down bias, but not both. The value is assigned at creation and is random. Therefore, pairs of random photons with the same polarity will be 25% of the time they will both be up, 25% of the time they will both be down, and 25% of the time they will be up and down, and another 25% of the time they will be down and up. Remember, this is for pairs of random photons with the same polarity. In other words, this represents experiment number 2 that we looked at. Recognizing that entangled photons are different, for pairs of entangled photons we assign equal bias. In other words, we have 50% of the time they're both up, and 50% of the time they will be both down. You cannot get an up and a down or a down and up with entangled pairs of photons. Rearranging 1, 2, 4, and 5 above and changing to decimal notation, we did this so that everything lines up and looks pretty. Number 7. Assigning cosine squared as the correlation probability to up, up, and down pairs and 0.5 probability to up, down, up pairs, we can derive the random results in 2 above from 1 above and vice versa. So what we're doing is we're replacing the up with cosine squared theta, and since this is a probability, we can multiply it by the frequency, add it to the other frequency multiplied by its correlation probability, and we will get this. For up, we again put in cosine squared theta, and down cosine squared theta, but over here it's only 1/4 and another 1/4, and that gives you 1/2. 50% of 25% is 1/8. You have 2 of them, you add them together, and you get your 1/4. So everything works very nicely when it comes to the math. So 8. If 7 above is true, then the entangled results in 1 above are a subset of the results from random photons. This would negate the necessity of non-local reality. So what we're saying here is we can take just regular old pairs of random photons, eliminate the up, down, and down, up. This 25% will go to 0, this 25% will go to 0, this 25% will go to 50%, and this will go to 50%. And so it will look just like this. So we can recreate this result using random and local results. Therefore, we really don't need non-local reality or spooky action at a distance. So, there you have it. Future videos, we're going to take a look at this in a lot more detail, a lot slower, take it a step at a time, and we'll probably use the level of high school math and high school science to be able to explain it. Additionally, I'd like to go into the physics of this situation, such as, for instance, the bias. What is that? What sort of properties can we assign to that? So until then, take care, and we'll see you later. Bye.